We are now going to look at differentiating expressions that are written in new forms. Please note that these techniques are not fundamental like the chain rule or the product rule, but they're instead just cases where we use the chain and product rules on expressions that are written in a different way to how we have previously seen them. First, we'll look at parametric equations. Let's say that we have a variable y, which is a function of x. We would usually write this as y is equal to fx. We can, however, choose to write this slightly differently and say that y and x can both be expressed in terms of another variable, call it t, and from the relationships between y and t and x and t, we can work out the relationship between y and x. For example, if y was equal to 2t squared and x was equal to 2t, we realize that y is equal to x squared. It would be quite pointless to express y is equal to x squared parametrically, but in some cases it can greatly simplify things. Let's say we have a set of parametric equations, y is equal to f of t and x is equal to g of t, which implies some relationship between y and x. Let's use the example y is equal to ln t and x is equal to 2t cubed. The question is now, what is dy dx? Solving this is actually easy. Like always, we identify what f of t and g of t actually are, and we write this down if we haven't already. Next, we find dy dt and dx dt independently. In our case, dy dt is 1 over t and dx dt is 6t squared. Like when using the chain rule, we aim to exploit the handy fact that multiplying dy dt and dt dx will cancel the dt's and leave us with dy dx. Be careful, we aren't just multiplying dy dt and dx dt, since this wouldn't cancel the dt's. We need dt dx, and luckily this is just 1 over dx dt. So we just flip our expression for dx dt to find dt dx, which in our case must be 1 over 6t squared. Now we multiply together dy dt and dt dx to leave us with dy dx. In our case, we get 1 over 6t cubed. If we wanted to not have this in terms of t, but instead of x or y, we would need to sub in to get rid of the t. Let's say we wanted dy dx in terms of x. Then we must rearrange our expression for x so that we get the t term in our expression. We are trying to replace 1 over 6t cubed. X is equal to 2t cubed, and so 1 over x is equal to 1 over 2t cubed, and so 1 over 3x is equal to 1 over 6t cubed. dy dx is therefore equal to 1 over 3x. Implicit differentiation is when we want to differentiate an expression that relates, say, x and y, but not in the usual form of y is equal to some function of x. Instead, the form will have many terms which may include both y's and x's, which all relate to each other in some way. To understand implicit differentiation, we first must ask the question, how do we differentiate a function of y with respect to x? For example, what is 2y differentiated with respect to x? The answer relies on the chain rule. First, we differentiate the function with respect to y, and then we multiply it by dy by dx. This cancels the dy's and leaves us with what we want. Differentiating 2y with respect to y is 2, and so d by dx of 2y is just 2 times dy dx. Let's use the difficult example x squared plus xy plus 4y squared is equal to y squared times sine x, where from this we want to know dy dx. The strategy is to differentiate each term at a time with respect to x and then rearrange the result. When we say differentiate each term at a time with respect to x, we mean apply the operation d by dx to that term. D by dx of x squared is 2x. So far so good. The next term is more difficult. Since we have two things multiplied together, we know we're going to need to use the product rule. We identify each term separately and differentiate them with respect to x. The y goes to dy dx and the x differentiates to 1. Applying the product rule equation, we get that this whole term differentiated is x times dy dx plus y times 1. Moving on to the third term, we are faced with differentiating 4y squared with respect to x. We will first differentiate it with respect to y, and then we multiply the result by dy dx. Moving over to the other side of the equal sign, we again have a product rule situation of two things multiplied together. Same as before, we identify each term individually and differentiate them with respect to x, and then we apply the product rule equation. Differentiating y squared with respect to x is 2y times dy dx, using the same method as before, and differentiating sine x with respect to x gives us cos x. We get that this term differentiated with respect to x is y squared times cos x plus sine x times 2y dy dx. The next step is to rearrange this expression to get it in terms of dy dx by getting all the terms including dy dx together on one side of the equal sign and factorizing the dy by dx out. Now we have our expression for dy dx, which, like the original equation, contains both x's and y's. I must emphasize that this is a very complicated example, but if you can do this one, you really can do any implicit differentiation problem.